Latent diffusion models represent a cutting-edge approach in the realm of artificial intelligence, particularly in generating highly detailed and creative content. At their core, these models leverage the concept of diffusion, a process where patterns of complex data gradually transition from a state of randomness to a structured configuration over numerous iterative steps. Unlike traditional models that directly generate outputs from inputs, latent diffusion models operate within a latent space. This latent space is an abstract, compressed representation of data that allows the model to capture deep, intricate patterns unseen in other techniques. By manipulating data within this space, latent diffusion models can create outputs with unprecedented detail and novelty, marking a significant evolution in the field of AI. This introduction aims to demystify the foundational components and principles underlying these models, setting the stage for a deeper exploration of their architecture, training methodologies, applications, and broader implications. The evolution of deep learning is a pivotal narrative in the advancement of artificial intelligence, laying the groundwork for the emergence of latent diffusion models. Beginning with the development of neural networks, deep learning has progressively unveiled capabilities in handling and interpreting complex data. This transitioned into explorations of generative models, where the focus shifted towards creating new, data-like instances, rather than just analyzing existing data. Latent diffusion models stand at the forefront of this evolution, integrating deep learning's nuanced understanding of data structures with innovative diffusion processes. These models benefit immensely from the depth and flexibility of deep learning architectures, enabling them to perform the intricate task of navigating through latent spaces. The role of deep learning here is twofold: providing the methodological foundation for managing high-dimensional data and laying the architectural blueprint for crafting the diffusion processes that characterize these advanced models. This synergy between deep learning's analytical prowess and the creative potential of diffusion processes fuels the groundbreaking capabilities of latent diffusion models, making deep learning's evolution essential to their success and continuous development. At the heart of latent diffusion models lies the concept of diffusion processes, a key basic concept crucial for understanding their functionality in machine learning. Diffusion processes, inspired by natural phenomena, describe a gradual transition from disorder to order, mimicking the way particles move from higher to lower concentration areas until they reach equilibrium. In the context of machine learning, this concept is adapted to handle complex data structures. Initially, the model introduces noise to distort the input data, progressively reducing this noise over many iterations to reconstruct or generate new data instances. This process is emblematic of denoising, where the model learns to reverse the diffusion process. By doing so, it can generate highly detailed and realistic outputs from a chaotic starting point. The efficiency and effectiveness of diffusion models, particularly in latent spaces, hinge on this intricate denoising process, setting them apart from other generative approaches in artificial intelligence. Latent diffusion models distinguish themselves within the landscape of artificial intelligence by incorporating a series of unique features that set them apart from other generative models. These models excel in handling extremely complex and high-dimensional data thanks to their innovative use of latent spaces. By performing the generative process in this compressed representation of data, they are inherently more efficient and capable of capturing subtler, more nuanced patterns that other models might miss. Moreover, latent diffusion models employ a controlled, iterative process of adding and then gradually removing noise from the data in the latent space. This approach allows for a more refined control over the generation process, yielding outputs with remarkable detail and diversity. The orchestrated diffusion process, combined with the strategic exploitation of latent spaces, enables these models to produce highly realistic and creative outputs, from intricate images to complex patterns, showcasing their distinct advantage in generating high-quality content with a level of precision and variability previously unattainable. At the heart of AI innovation, especially within the domain of latent diffusion models, lies the concept of the latent space, a transformative element that holds the key to unlocking unparalleled detail and novelty in generated output. This abstract, compressed representation of data is pivotal, as it allows for the intricate encapsulation and manipulation of information far beyond the capabilities of traditional generative models. The significance of latent space in artificial intelligence transcends mere data compression. It provides a canvas for the complex interplay of data points, where the subtlest of patterns can be discerned and amplified. In latent diffusion models, this space is navigated with precision, guiding the generative process to achieve outcomes with depth, complexity, and creativity unavailable to conventional processes. This makes the exploration of latent spaces not just a methodological choice, but a strategic advantage in harnessing the full potential of AI to create, innovate, and reimagine the boundaries of content generation.